So the first piece of our big idea working toward this dimension of a vector space has to do with linear combinations and spanning sets. So this first definition at the top of the page is just explaining what we mean by a linear combination. So this is that same, I was avoiding linear combination earlier, but I was talking about decomposing a vector into a combination of other vectors, and that's the same thing that this is talking about. So we have vectors v1 to vn. A linear combination of those vectors is just something of this form where we're taking any scalars, the AIs are scalars, times a vector, adding those things together. So that's called a linear combination. All right, so for example, I can do 2 times 1, 0, minus 3 times 5, 4. That's a linear combination of the vectors 1, 0, and 5, 4. Okay. So once we know what we mean by linear combination, then we can define a spanning set. So that's the second definition here. All right, so our spanning set, S is going to be our set, and it's a set of vectors, v1 to vn, and it looks like I lost my set brackets there. So S is this subset of vectors, v1 up to vn. S spans v, that's what we're defining here, if for every vector v, there is a set of scalars, a1 up to an, so that we can write v as this linear combination of the vectors from S. Okay, so in more words, fewer symbols, S spans v if every single vector in v can be written as a linear combination of vectors from S. All right, so we're thinking of that set S at the top as our building blocks. So we take those building blocks, they're vectors from V, but look, it's only a small collection of them in the way this definition is written. It's a finite collection. So this small collection of vectors V, using this linear combination idea, any scalars we want times the vectors and add that up. What spanning means is that we can build all of V that way. So we can build anything in V out of just that collection of building blocks along with all the scalars that we have. Okay, so that's what it means to span. So we're going to do a bunch of examples, things that span and things that don't. So for example, 1, 0, 0, 1 as a set spans R2. And the reason why is because we can take any vector in R2, and any vector in R2 takes this form. It's AB, and we can write it as a linear combination of those two vectors. Okay, and so that shows that any vector in R3 can be written as this linear combination, can be built out of those building blocks of 1, 0, and 0, 1. All right, another example. The set 1, 2, and 2, 3 spans R2. So those building blocks up above, the things that we called I and J, 1, 0, and 0, 1, those span R2, but that's not the only way we can build R2. We can also build R2 with these two vectors, 1, 2, and 2, 3. And this is an example that we did before. So I'm going to just kind of remember where we saw this before. So before we wrote AB in terms of those as a linear combination, and the way we did it was we built our scalars that we needed out of the A and the B. And it turned out that what we needed was minus 3A plus 2B times 1, 2, and 2A minus B times 2, 3. And you should be able to kind of check that in your head, think about distributing and adding those vectors. So this is another spanning set for R2. All right. Just to throw a little wrinkle in this that we'll come back to later, I'm going to plant a little bit of a seed here. The set 1, 0, 2, 3 Ooh, that 3. Let's fix it. Okay. And then 0, 1 also spans R2 because, again, I can take a generic vector in R2 and I can write it as A times 1, 0 plus 0 times 2, 3 plus B times 0, 1. And notice this one's a little different because I didn't actually use the 2, 3 vector. I just put 0 of them in there. I could use it. I could instead say something like, let's see, let's try to use one of the 2, 3 vectors and see what we need. So then I think A minus 2 will work for 1, 0, and B minus 3 times the 0, 1 vector. So this is just showing a different way that I could write AB if I wanted to. You might have caught on that actually I could do that a lot of different ways. There are plenty of ways I could make that work. And so that's a little different maybe than the ones up above. All right, let's try a non-example. All right, so a non-example. The vectors 1, 1, and minus 1, minus 1. So this set does not span R2. Okay, and one way to see that is to say, all right, if I'm going to take those two vectors and I'm supposed to be able to make any vector out of them, what does any vector out of them look like? So if I thought about all possible linear combinations of these two vectors, I would take some scalar, I'm calling it x times 1, 1, and I'd take some other scalar y times minus 1, minus 1, and I would be adding those up. And if we add those up, we get x minus y, x minus y. So the span of those two vectors looks like this. So this is the span of those vectors 1, 1 and minus 1, minus 1. Okay, but notice what the span is very particular. Like the x minus y and x minus y there, those are the same. Okay, so that means we can build, for example, 7, 7 or negative 15, negative 15. That's not going to be a problem. But what we can't do is anything where the first term, the first component, and the second don't match. I'm not going to be able to make x minus y be 1 and x minus y be 2. So really, we can't make any a b unless a equals b. And so these don't span R2, they span only like that x equals y line on R2. They span only the set of vectors that have an x component and a y component that are the same. All right, I want to do a few more spanning sets from different contexts. So that was all in R2, but let's look at some things like Q adjoin root 2. Okay, so, oh, sorry about that. Kicked in Siri. All right, so Q adjoin root 2. I want to think about a spanning set for this. Okay, so one thing to remember here is what are our vectors and what are our scalars? So the vectors were things of the form a plus b root 2, where a and b are rational, and our scalars were the rational numbers. Okay, so the idea like above is the same. I'm going to say let's take any arbitrary vector, so that in this setting looks like a plus b root 2, and I'm going to try to write it as this linear combination. I want a scalar times a vector plus a scalar times a vector. And I want to keep doing that as much as I need to. Okay? And the scalars here are supposed to be from Q, and the vectors here are supposed to be from Q adjoin root 2. All right, and it turns out there's a really easy way to do this because we sort of do it already. Look at what we have that's already in Q. A and B are in Q, right? So let's just put those here. A, that's a fine scalar. B, that's a good scalar also. And now in the straight underline here, the green arrowed part, I'm trying to put some vectors that are going to be my building blocks. And those building blocks, look, all I need to put in here is a 1. That's a fine vector out of Q adjoin root 2. And then in the second one, I need to put root 2. Again, that's a vector in Q root 2. That's no problem. So when we write down A plus B root 2, we're kind of already decomposing it. And what we're using as our spanning set is 1 and root 2. So let's try one that's similar. So instead of Q root 2, let's do Q adjoin root 2 root 3. Okay, so remember our generic vectors here, those were the A plus B root 2 plus C root 3, and then because we needed to be closed under multiplication, we also had to add in root 6's. So we added in a D root 6. And now you might be jumping to what you want to do here, which is pull this apart into pieces. I need a scalar from Q times a vector. I need a scalar from Q times a vector from Q adjoin root 2 root 3. I need a scalar and a vector, and I need a scalar and a vector. So it looks like we haven't done anything here, but all we're saying when we write those 4 terms, we're already having in mind a spanning set. Our spanning set here is 1 because I need to allow a rational term, root 2, root 3, and root 6. Okay. Great. So now in the next video, we'll talk a little bit more about these spanning sets and why this one up here was a little bit different than the other ones.